So today we're gonna see what happens when molten iron touches this magnet. So what I've done here is I've stuck the magnet to a piece of metal in the ground so it's parallel to the thermite. So when it goes off, we'll see if the metal stream gets attracted to the magnet or not, and if it doesn't, it'll just fall straight to the ground. We'll see if it bends. All right, here we go. 3, 2, 1. So that thermite turned the wooden bowl into a raging firestorm, but I'm beginning to think that there's no reaction between molten metal and magnets. In fact, I think that molten metal and magnets don't mix very well at all. That was pretty cool. I might have broken my magnet though. It was completely engulfed in the flames right there. But it's not very hot. Okay, it's kind of hot, but not like destroyed hot. Once magnetic materials reach a certain temperature, they lose their magnetism. That's 600 for this magnet and 1400 degrees Fahrenheit for iron. This is called the Curie point, and below it the magnetic fields are nice and aligned, but above it they're totally random. This is why we don't see any attraction between the molten iron and the thermite. The iron hasn't cooled enough to align into a magnetic field yet.
What they're trying to do is find out how the Earth's magnetic field is generated. And some of the first scientists to study this, starting with William Gilbert in 1600, proposed that the Earth was a huge permanent magnet. Now today we know that the inner core of the Earth is solid and it's mostly made up of iron and nickel, which are ferromagnetic elements. However, the temperature of the inner core is nearly 6,000 Kelvin, which is way above their Curie temperatures, and so there is no way that they could maintain a permanent magnetic field. The same is true of the solid mantle of the Earth. Much of it is way too hot for permanent magnets, which leaves only the liquid metal outer core as the place where Earth's magnetic fields could be generated. And this is what is modeled by the 3-meter spinning sphere of molten sodium.
And we use liquid sodium because it's the best electric conductor of any liquid.
Lodestones, also known as magnetite, is a naturally occurring magnet found everywhere on Earth, and was used in making the very first compasses. It is observable and testable.
As its name would suggest, the mineral magnetite is magnetic. Notice that a magnet sticks tightly to a sample of magnetite.
The process by which lodestone is created has long been an open question in geology. The leading theory suggests that lodestones are magnetized by the strong magnetic fields surrounding lightning bolts. This is supported by the observation that they are mostly found near the surface of the Earth, rather than buried at great depth.
So why do all magnets point north? The largest concentration of magnetite is of the magnetic north. There is evidence they are hiding a secret north continent. The North Continent was hidden around 500 years ago. Around the same time the globe model became generally accepted. They had been hiding the North and South from us for a very long time.